parametric function that the Lagrangian takes in and spits out an energy for, or if it's just a Taylor function, like a parametric vector function that's out potential, or if it's just a relation that you just integrate over some 2D versus a line in some 2D space that you have a 3D function for, I guess. Height. That's weird. All right, it's tough to explain.
Okay. It's anyway what she was asking. Okay, that's fine. That's fine. But I certify that the question is very much related to what we are doing in the class. So we are I just see here in the chat it's supposed to have. So we do set up a goal to describe electrons and molecules that form orbitals and define energy levels, right? And we need equations that will control them, right? We already did a playing with a toy in our mind. It was not a real toy about rope, and now we need a wave equation that would work for the electrons in the molecules or in atoms. And before we declare this equation, if you're curious, you can look on Wikipedia or in any text showing the equation. But we want to establish solid foundation for this equation, and we need to understand weight of what. Okay, electron is weight, but weight of what? And what each wave has its frequency, amplitude, phase. So what is phase? If you look on a wave of electrons, what is changing as we go through the timeline or through the path? And from this point of view, we are trying to establish connection with this paradigm of classical mechanics with our intuition when each object as a particle goes in a path, right? And a wave. So suppose we have a particle electron that may go as particle or as a wave, and then we want to explore what is the shape of wave in different positions, in different distances from the center, and why some of this wave will have positive, negative, or zero values. So one can attack philosophically, mentally this problem by thinking that electron was traveling from its original point to the point where we explored by different pathways. And along the path, it accumulates something, accumulates phase. And this phase, which can be longer or shorter, defines whether the wave will go into the positive, negative, zero, to the path from initial to final point, determines what it is. Now, mathematical tool and our assumption that I will go over again many times will be that along the path, an electron accumulates action, which is computed in the same way as it would do in classical mechanics. Okay? And now the question of James. The question was very tiny. I appreciate it. Like, is it just an integral or integral along a line? Right? So I just convert his question. Of course, it is integral along a line connecting initial and final point. Right? Make sense now? And if one wants to be very general, not a straight line, does not need to be straight. It can be a wavy line. And the length of a line, its curvature, defines what will be the action along this line and what will be the phase of wave function of a wave that we are going to explore. So basically, I summarized everything we need to talk about today. You will not hear anything else, but I will give some illustrations or try to look at this from different point of view. Yeah, thank you, James, for sparking this this discussion. Let me look on my slides myself because I may have forgotten what is there after being so involved in the discussion. So this is an outcome of probably should be a little less humble while speaking in front of the slides. Okay, here's myself. So here are the equations that we need to get by the end of Friday. Today, we are not going to complete them. And the Schrödinger equation is the main tool of this course. So in some sense, the course is like story about Schrödinger equation or application of Schrödinger equation to the chemical systems. But it is so important that you can work with them. There was already a no typo, so it should be the same symbol here and there. So since it is so important and all properties of individual molecules, if we skip statistical mechanics, so all properties of materials and sensors, if the individual and their ensembles are defined by Schrödinger equation in one or another way. So it is so important that we may invest, we may sacrifice like 6-7 meetings just to get the origin and basics, how it is derived and where it comes from. Because it is a subject why quantum mechanics is considered counterintuitive. And one can do homeworks, exams, quizzes on applications, but foundations are they are not in a regular teaching strategy. It's more something that people on humanities and philosophy do. There are opposite opinions, there are different interpretations. So I'm up to developing the equation. We are in more like in humanities. With some examples. Later on, after we postulate the equation, we will get more and more practical and specific. This, we will not arrive to it today, by Friday for sure. So we will be somewhere between third and fourth equation by the end of the class. And maybe I will just speak very long about these outcomes, and then we either discuss stuff in a freestyle or I'll just quickly jump through the slides. So today we were discussing waves, and we were assuming that waves are real, not in common sense, but in sense of mathematics. And it is everything we can touch in the real world is real mathematically. But there are imaginary numbers, right? Square root of -1, right? And the waves that electrons distribute are explained like 10 times easier if one uses the concept of complex numbers. So we need to revisit it. Probably you all reiterate and you know how to treat them, but I will better reiterate basic stuff in like 5-10 minutes. And here, please raise your hands if you have ever seen this first equation in the box. 1, 2. So, okay, then for those who have seen, what's the name of the scientist who designed it? Yes, okay. So Euler equation. So the I stands for imaginary, right? So the cosines, real cosine and imaginary sine, form the exponential. And we will speak about it and try to deliver it or go through background material. It is something like alphabet to the rest of what we will be doing through the semester. So no quantum chemistry without complex numbers. It's impossible. So next one is the royal idea. So the idea that today in class we need to give credit to James was originally stated by Prince Louis Napoleon. So he was assuming that electron is a wave, And then generations of scientists decided that action that was known for 100 years since the time of Napoleon is the best thing to plug into this exponential, and that if you be given the wave that corresponds to electrons. So it's only like summary declaration. I plan to go into details for it. So then, have you seen the movie Oppenheimer? Okay, I did. But I was in the scenic places where it was shot in the New Mexico. It's even better than it is in the movie. But main character Oppenheimer was colleague of Feynman, and Feynman got his major credit not for doing weapons, but for in simplified way for this equation. So if you understand this equation by the end of the class, you all are worth of Nobel Prize, maybe 70 years ago. So what is here? Suppose, when I was sitting there, I was showing, suppose we know electronic wave at initial time, how it is distributed, the shape of electronic wave. And we do want to predict future in mathematical and scientific sense for tiny object. So we want to know this distribution at final time. And the stuff that includes total energy and integral, very similar to the way how action is composed, allows to convert past into the future. This formulation of defining waves of electrons is more philosophically correct, and it is more general. But for solving chemically relevant practical problems, it is too heavy and often unsolvable. So the Schrödinger equation, which was originally stated and defined earlier than this equation, but it is a very simple mathematical consequence of the Feynman way of predicting future. So if we believe this equation, there is like 2 lines derivation of the Schrödinger equation. Before we go forward to details, I want to make a note to those of you who have already seen Schrödinger equation. Who has seen Schrödinger equation before? What? Congratulations. then everyone doesn't care of personality. So if one goes into Wikipedia or in simple texts, one is speaking about atomic or molecular orbitals, SPD, their shapes, their energies, and so Schrödinger equation is stuff that predicts them, right? Which is not wrong, but it is like only a small part of the picture. So if you need SPD orbitals and their energies, or molecular orbitals and orbital diode, whatever, those are static objects. Those are stationary waves that just exist if the system is not perturbed, if it is not interacting with a stove, external light, clean hands of an experimentalist. So which is like too much of idealization. In real world, there is a development forward in time. All things are changing dynamically, and then electronic clouds do change in time. So it's not just Schrödinger equation, but time-dependent Schrödinger equation that explicitly has dependence on time and derivative over time. And this is more general thing. So if we go from predicting the future to time-dependent Schrödinger equation, then we are set to go into actual content of the course. Questions? What is the lunch time? Finishes sooner. Okay.
What is that funny equal sign under Broglie?
The Broglie didn't wrote. He was not writing questions. He was just handwriting. And
Does it mean proportional to, congruent?
proportional. It is when we will be exiting the class, not today, but at the end of the semester. You're not going to show this equation to anyone. It's more like a trampoline and intellectual step to justify the next equations. So and in the ACS certified exams, no one will ask you like write an equation for the Bohr wave. No, it's only an imaginary concept to understand the next steps. So if I will write equal, it will be wrong. If I put nothing between them, then there will be no reason to show it. Why I'm doing this? This equation is very helpful to understand general concept, but it is wrong if you want to be precise, because it assumes that there is only one path, right? And in fact, electrons can go into opposite paths and they can correlate with so one red hat fairy tale. Yes, have you heard about it? Red hat fairy tale. I think it is international. It is in every culture. Anyone speaks French? Le Chapeau Rouge. So it is a fairy tale when a little girl is going to visit her grandma and meets a wolf on a path.
Oh, Red Riding. Oh, Red Riding Hood.
Red what?
Red Riding. Red Riding Hood. Red Riding Hood. One of the two.
Little Red Riding Hood.
Yeah, that one. Or Red Riding Hood.
Okay. Cool. Okay. So both the main character and the wolf did arrive to the same place, right? But they went different pathways. The electron can arrive to the same place by different paths, and one needs to add together actions corresponding to different paths. And if one would try to explain it in such short summary, this equation will it will be incomprehensible. So do not try to catch me or equation of being over. It's only like perfect sign. Yeah, but thank you for the question. I think it is really good to help all of us to okay, about half of the time is finished and I'm just starting the meeting. So we need to recall it, right? I just do not know how to stop the okay. It disobeys me a little. It was playing on home computer. So if one, it is what we told about double slit. So there is a movie. If you see it downloaded figure, it forms the fringes as it developed. So it is what we did last time. And there was a missing derivative sign in the last equation when we did a little recitation of the least action principle. So briefly, if a particle travels a certain path, then one can set up the single number that will summarize all details of a path. So L is kinetic minus potential, x of t is path, initial time and final time. But if one changes the path, the action will have different value.
So is x a vector then? Is x a vector?
X is a function.
Okay.
Like at each point of time, x has a certain value. So it's multi-dimensional vector.
Okay, that makes sense.
Vector of infinite dimension. Rigorous mathematicians would tell that it is a we would put rectangular brackets of x of t and tell that s is a function of a function. But right now we don't care over these details. So dimensionality of the angular momentum. I'm trying to speak too quick, and please stop me if you think I'm telling some irrelevant things. I'm balancing comprehension of materials and having a friendly and inspiring discussion and covering certain amount of materials. So we were speaking about Bohr model, superficially without details, that it has some fringes along the path, and the amount of fringes is proportional to the angular momentum. And only certain values of angular momentum are permitted. So the Bohr model was formulated that angular momentum takes discrete values. Okay. Now, what is the dimensionality of angular momentum? So on one, this is an exercise that we all can do together and just rushing through to complete in time. So position is distance, momentum is mass times velocity, distance over time, right? And then we have distance squared, mass over time squared, and if we process kinetic or potential energy, let's try to do like gravitational energy of an object. So it is mass. This is just distance, and what is the dimensionality of the acceleration? So it is right? Correct? Okay. So does it, a mistake, it should be also T here. So this portion looks like an energy, right? Mass, distance squared over time squared, and then we can consider it as to have the dimensions equal, we need to multiply it by time. So it is equivalent to energy times time. So why do we need to focus on this trick? Dimensions of angular momentum are the same as dimensions of energy times time.
Actually.
Yes, it is dimension of action. So action and angular momentum have the same dimension. Why do we waste our precious time on this little observation, this little exercise? If you believe into Bohr's model, right, then the stuff that accumulates along this revolving paths is angular momentum defines the phase of the fringes in the Bohr model. So angular momentum is related to electronic waves on the other hand. But through this exercise, we see that action that accumulates along the trajectory also defines the phase of the wave function. Yes? Can you do it? So action defines the phase of the wave function. And then if we dive into this little exercise, we can tell, we put like sine or cosine action in the as an argument until it will be our electronic wave. Okay. So now we do, I wouldn't say break, we switch the gears. We need to speak about slightly different thing. So so here is a summary of what we talked about. So we put action, we divided by Planck constant to make it dimensionless, to be reduced Planck constant so that it will be dimensionless in terms of angular, like radians, and then it will be something like wave function. But just try to do it. You can check me later. Is that if we assume that electronic wave is real, we will get too much complications and even some unresolvable paradoxes. It is much healthier to assume that the stuff that is oscillating for electronic waves has a complex nature. Complex not it's so complicated. It is mathematical terminology. So how did humankind design integer numbers? I think we can sacrifice space, but you will have a discussion. You're not yet tired of me. So suppose we observe human society like 20,000 years ago, or whatever, and people have objects, like apples or rabbits, and one can count them with natural numbers, right? 1, 2, 3. But as soon as people start getting little conflicts and try to deprive objects from each other, mathematical subtraction, one can get the negative amount. Like I owe you 5 apples. I have -5. So it makes a new mathematical operation, gives a transition from one type of variables to another one, from natural to intelligent. Then if we get a knife and start chopping objects, then it will be fractional numbers, rational numbers, right? But they are all real. If we make an axis, we can say, okay, half apple, 3 halves, whatever. Right? Again, mathematical operation of division brings us to a new domain of numbers. And now if we start making a square root, we get another new domain. Like if we need a square root of -1, we get something that we cannot put on a single axis. Right? So we need another axis. By the way, why square root was designed? What's the reason for humankind to design square root? It's a question more for boys than for girls. So from time to time on Earth there are nuclear conflicts, there are some development of weapons, right? And there are some like catapults, cannons, right? Where one needs to predict where the projectile will land. So there is if one solves middle to high school problem of mass traveling in gravitational field, right? It is a main problem of designing of predicting where projectile will land. So it's the problem came not to torture high schoolers, but to predict like a little nuclear activity. Okay? And to find where projectile will land, one needs to solve quadratic equation. And once solving quadratic equation, one designs this square root operation. And sometimes the discriminant is less than 0. Artillery boys tell there is no solution, but mathematicians tell that the solution is in the imaginary domain. Right? So we do have by solving the quadratic equation here, we get a solution plus minus I, right? So there is a common way to believe that special class of numbers, complex numbers, are two-dimensional vectors. So there is a real component and imaginary component, right? And one typically writes these two vectors as real multiplied by 1, imaginary multiplied by I, where I is assumed to be this square root of -1. So 2 complex number can be expressed as a point on the two-dimensional plane. Rectangular treatment of these complex numbers is correct, but not always convenient. There are many practical applications where complex numbers are changing, or one needs to consider complex numbers that do have the same length of this vector and change only angle. And in this situation, one needs to make transformation between rectangular to so-called polar coordinates. By the way, I know you can be tired, irritated. What are complex numbers are used in addition to physical chemistry?
Rotation. If you multiply a complex number by another complex number, it rotates it by the angle that the first one's on.
That's correct. But which areas of this is correct? Which another area of human activity?
Like stuff to do with like electricity.
Yes, yes. Electrical engineers, when they do have power plants, right, there is a developed technology to calculate electric signal in terms of complex numbers, assuming that it is not just cosine oscillating, but it is a rotation in complex plane. And for signal processing, for like your musical center with equalizer, high quality, it's all in the complex plane design. So it is, unfortunately, we are not pioneers. Engineers are at the same page. So you're fine with right angle triangles, right? Pythagorean theorem, right? And expressing, defining sines and cosines. So cosine is the one that is near the angle related to the length of the vector, right? And sine is the length of the one that is away from angle related to the length of the vector. Let's interview so here's the talking stick. What's the sine and cosine? I do not doubt your knowledge. I just want to hear the right language.
Functions.
How to define sine and cosine based on sides of triangle with right angle?
Oh, sine is the opposite side of the other lines. Cosine is the adjacent side of the line.
Just opposite and adjacent. Thank you. It is what I wanted to hear. Opposite and adjacent. And now we can invert definition of iron and tell that opposite is hypotenuse times sine, right? And adjacent is hypotenuse times cosine. But now, if we are not just simply two-dimensional plane geometry, if you think about complex numbers, then you can tell that those are real and imaginary part of a complex number, right? Hypotenuse is the length of this vector, and then the complex number is the length of complex vector times real and imaginary part, which will be sine and cosine. But this part is some sort of dimensionless, right? For doesn't matter what is the length of the vector, we can speak only about the angle. So if we divide complex number by its hypotenuse, its length, then it will be this cosine phi plus I sine phi. Okay. So it's a little challenge for human laziness to write this long cosine and sine. One can just symbolically combine them into into this notation. In case we do not have imaginary part, if you agree with our typical exponential, if there will be, if there is no imaginary part, it means if sine phi equals 0, it means phi equals 0, and if phi equals 0, our regular definition of exponential will give 1, and cosine of phi equals 0 is also equals 1, right? So it will coincide with our regular definition of exponential, but outside of this phi equals 0, it gives us a point on a circle with a radius equals 1. Any questions? You're fine, you're against it, you don't care. You care, but you're not 100% confident. Just give me a little sign that I know how to. Okay, no energetic objections, but it's not your active vocabulary to use every day. Yes.
Okay, so the E is to the I of phi of B there. So is that, well, I guess this, but so that represents basically the real wave function also added to the imaginary one exponential.
You are correct. You haven't said anything wrong. Okay. But the wave function is complex. It has real and imaginary part. It's healthier to think this way. Okay. It's not real wave function, real part of the function plus imaginary part of it.
Okay, and then the way the wave goes isn't really like stationary and like a linear line. It's more of an exponential type of wave.
So
It's either like the
be very soon, maybe, well, I'm not sure, maybe today, maybe on Friday, we'll get our properties of wave function. And one of them is that wave function corresponds to wave function square corresponds to probability. If you have only one electron, the probability that electron will be elsewhere in the universe is 1. Right? So the wave function is normalized. It cannot exceed the integral of wave function everywhere, cannot exceed 1. Therefore, this thinking about exponential growth is not very relevant. We will have very low values, typically below 1 everywhere. It's more important to think like where it will be 0 or non-zero because of the fringes, because wave function always oscillates. But thank you for thinking and trying to match it together with our common sense understanding of explanation. Now, if we start again, it's not an exact equation, James. It's only a trampoline. But if you start shaping up our understanding of wave function as exponential with an imaginary phase, and phase is action divided by Planck constant, we are getting closer to defining or to understanding what is a wave of electrons. Okay. So there is no time for this, but it is, I wouldn't say my favorite exercise, but I did a discovery, personal discovery for myself. As most normal people, not highly skilled in math, in the high school, I was hating trigonometric relations. I think majority of class attendees will be on the same side. So by some reason, our high school instructors torture us to making this converting sum into product and backwards. We all carry a lot of not very positive feelings about it. And I thought, okay, it's I'm so happy I survived. I don't need to do it after going to college. And then suddenly I found that instead of like after reciting complex variable calculus, I cannot say it's my personal discovery. Humankind knew it, but I rediscovered for myself that one doesn't need to memorize any of the trigonometric identities. One needs to know only basic property of exponential multiplication, and then one can rederive all of these relations. So we have about 4 minutes. This would take 15 minutes. But I'm just giving you a hint. If you find yourself on the, which is improbable, on the inhabited island without internet, and you need and you do not have internet for trigonometric relations, there is a way to rewrite them from scratch, just on a piece of paper within a few minutes. So on one hand, we know that multiplying two exponentials is equal to exponential of summation of their arguments, right? If those are imaginary exponentials, we can replace both first and second line by Euler equation. And Euler is a blind German mathematician. These days, a lot of people go to United States seeking for prosperity and careers. In whatever 1760s, there was a little rise of Russian Empire, and some people were seeking profit there, and Euler moved there. So it's interesting trajectory. Then, so if one places Euler equation for the first and second line, here we have cosine of sum, here we have sine of sum, and here we have a product of complex number composed of real and imaginary for alpha and for beta, right? Then one can open brackets for the second line and identify real part by multiplying first and first, and then last and last, and second part, right, which will be real. And then cross terms will be imaginary part. And then by two complex numbers are equal if real part of first is equal to real part of second, and complex part of first equal to complex part of second. And then from this, one re-establishes this equation that we used 2 classes ago, and that our high school teachers were drinking our blood for 2 years. Okay. If one multiplies two complex numbers with opposite phases, the result is 1. So E minus A, E to the power minus A times EA will be 1, right? Because E to the power A minus A will be E to the power 0 equals 1. Same with imaginary. So this property is used very broadly in physical chemistry and quantum mechanics through the following operation. The little star sign here means take whatever your complex number and flip it, make a mirror image in respect to the axis. So the star means real part is the same, imaginary is different. If one multiplies them, one can see that it means rotating forwards this angle and then rotating backward this angle. You'll see that rotating forward and backward will give you a real vector. If the lengths were 1, then the answer will be 1 for sure. So the complex number, if the length of complex number is equals 1, then Z star times Z will be 1. And this property will be used shortly. Okay, 1 minute left. So wave, if you take this electronic wave, if you take it conjugate times itself, it will be by wave function squared, absolute value, and its meaning is probability that electron is placed in is found in a given location around space and time. And it is a definition of wave function. So we work on mathematical symbols, mathematical equations for wave function, but wave function itself is just the abstract concept. But if one takes it absolute value squared or wave function conjugate times itself, it will be something that we can interpret as probability to find an electron at a specific position of time and space. We'll continue on Friday. And the meeting is done. We don't have lab for this class, but the room is used for a little session on Python and computational language and machine learning. You do not need it for the class, but if you're curious, you're welcome to stop by the room. We start regular labs in a week after the third day. No homework, we still in the philosophical stage, and looking forward to see you. I'll stay here, answer questions if any, but everyone is welcome to disconnect and depart. Yes, because everyone takes huh? Yes. I will share the recordings to everyone. Yeah.
I have a question.
Oh, please.
I didn't want to ask the question.